As mentioned in one of the earlier videos on noise sources, pink noise falls off at 3 dB per octave or 10 dB per decade. Since in many cases we will want to take the output of our pink noise filter and filter it some more to give a random signal, a sub-audio noise signal as it were, we probably want to make the corner frequency of this filter fairly close to the lower end of the audio range, so around 16 Hertz. Unfortunately, you can't really build a filter directly with analog hardware that will roll off at 3 dB per octave. A single pole filter will roll off at 6 dB per octave, and you can't really build a half pole filter. So we have to do something to approximate a minus 3 dB roll-off. There is a standard circuit that's been around for many decades. I first saw this circuit in probably about 1974, and the circuit we're going to use is very similar to this. I have tweaked it just a little bit. Do note that it does have the standard 1K output impedance that we have talked about elsewhere. Although a detailed mathematical analysis of the impedance of the feedback network is really an exercise for first semester circuit students, an intuitive understanding of the way this works is a little bit trickier, and we'll go into that in our next video. For now, we're just going to introduce the basic circuit. After modeling this circuit with several combinations with slightly differing resistance values, I found that 330K really gives a better fit to a minus 10 dB per decade roll-off than does the 270K. So that's the major change that I have made in this circuit. If you look at a modeled response for this slightly modified circuit and compare it to our minus 10 dB per decade starting at 16 Hertz, you'll see that it's a fairly good fit. It sort of goes up and down around the ideal, but it never strays too far from that. Also, if you look at the difference between 20 Hertz and 20,000 Hertz, that's basically the range of human hearing. That's a total of 3 decades, and so since the roll-off is minus 10 dB per decade, then we should be down by about minus 30 dB at 20 kilohertz relative to 20 Hertz, and if you look at that, we're pretty close. Also note that below about 15 Hertz, the response is relatively flat. Now, one thing we need to do is we do want our standard plus and minus 5 volt output. Again, this is a noise signal, so we will not get that exactly, but we probably want to get it close. Now, it turns out that a gain of about 3 at DC will get us close to our 5 volt amplitude. Since at DC the two capacitors are acting like open circuits, the only thing in the feedback network is the 330K, and so that would mean we need about a 100K as our input resistor to give us that gain of approximately 3 at DC. Now, this is not going to be exact. It will depend on exactly what the amplitude of your white noise input signal is, and if you modified the filter network and the feedback loop, then you might need to modify that input resistor as well. But 100K will get us pretty close. With that determined, we can calculate the compensation resistor. At DC, all you've got is the 100K input resistor and the 330K feedback resistor. The capacitors are acting like open circuits, remember. And so if you do the parallel combination of those, the closest 5% value is 75K. Now, if we wanted to have a little bit better control over the final amplitude, we probably want to put a fixed resistor in series with a trimmer potentiometer in the input, and the values here aren't terribly critical. I have chosen 39K and a 100K trimmer, and that will probably be sufficient if our white noise signal really is close to a 5 volt amplitude to give us close to a 5-volt amplitude out for our pink noise. If you got this thing built and you found out that you could not adjust it far enough one way or the other, then you can adjust that fixed resistor as necessary. That is our basic pink noise filter. In the next video, we will discuss how to actually understand why this filter does what it does.